Hello, welcome you all for the lecture of Z transforms. Z transforms has its applications similar to that of Laplace transform. Laplace transform is for continuous systems, but Z transform has its applications in discrete system analysis. Let us see the definition. If Un is a function for discrete values of n is equal to 0, 1, 2 and so on, and un is equal to 0 for n less than 0, then Z transform of the function un is defined as Z transform of un is equal to summation n is equal to 0 to infinity un z raised to minus n. So this is Z transform of function un. Any function, un may be any function, discrete function. Now, and this Z transform of un can also be written as u bar of z. So Z transform of un is equal to summation n is equal to 0 to infinity un z raised to minus n, which is equal to u bar z. Now if we shift this Z transform to other side, then we get inverse transform. So inverse of Z transform is written as un is equal to inverse transform of u bar z. Now let us see Z transforms of some standard functions. Let us find the Z transform of k to the n first. So now Z transform of k to the power n. Here k to the power n is nothing but our un. Okay. So let us find the Z transform of k to the power n by applying the definition of Z transform. Now, as we know, Z transform of un is nothing but summation n is equal to 0 to infinity un z raised to minus n. So replace un by k to the power n as we want to find the Z transform of k to the power n. So Z transform of k to the power n is nothing but summation n is equal to 0 to infinity. In place of un, we are writing k to the power n and z raised to minus n as it is. So now rearrange the terms. We get this is equal to summation n is equal to 0 to infinity k by z whole raised to n. And so expand the summation by substituting n is equal to 0, 1, 2, 3 and so on. For n is equal to 0, we get k by z raised to 0. K by z raised to 0 is nothing but 1. Then for n is equal to 1, k by z. For n is equal to 2, k by z whole the square and so on. So now this series we can see is similar to 1 plus r square, which is a geometric series with a common ratio r. Here r is nothing but k by z. So the sum to infinity of this geometric series 1 plus r square is nothing but 1 upon 1 minus r. Here r is nothing but k by z. So Z transform of k to the power n is equal to 1 upon 1 minus k by z. So when you simplify this, you get z upon z minus k. Therefore, Z transform of k to the power n is nothing but z upon z minus k. Now let us find Z transform of 1. So to find Z transform of 1, let us use the previous result. So we already have the result Z transform of k to the power n as z upon z minus k. In this, put k is equal to 1 because we want to find the Z transform of 1. Put k is equal to 1, we get Z transform of 1 to the power n is equal to Z transform of 1. 1 to the power n is nothing but 1. So in right hand side, you replace k by 1. So we get z upon z minus 1. So Z transform of 1 is nothing but z upon z minus 1. Now, let us prove one more result. Z transform of n to the power k is equal to minus z into d by dz of Z transform of n raised to k minus 1, where k is positive integer. So to prove this result, let us consider RHS first. So RHS is nothing but minus z d by dz Z transform of n to the power k minus 1. Now minus z, keep it as it is, d by dz as it is. Here we need to write Z transform of un because here un is n raised to k minus 1. So now I write the definition. According to the definition, write the Z transform. Z transform of un is nothing but summation n is equal to 0 to infinity un z raised to minus n. Here our un is n raised to k minus 1. So n to the power k minus 1 z raised to minus n. Now this is equal to minus z as it is. Take this derivative sign under the summation sign. Summation n is equal to 0 to infinity. N to the power k minus 1 is constant, keep it as it is. And we have to differentiate with respect to z. So z raised to minus n, we are differentiating with respect to z, we get minus n, z raised to minus n minus 1. So now this becomes minus z as it is, summation n is equal to 0 to infinity minus n raised to k, because n raised to k minus 1 minus n becomes n raised to k, and z raised to minus n minus 1, keep it as it is. And this z take under the summation sign and simplify. You get summation n is equal to 0 to infinity n to the power k as it is, and when you simplify these two you get z raised to minus n. Now this is nothing but, according to the definition, summation n is equal to 0 to infinity un z raised to minus n. Un z raised to minus n is nothing but z transform of un. Here our un is n to the power k. So we get z transform of n to the power k. This is our LHS. So we proved the result. Now let us find z transform of n. Already we know the result, z transform of n to the power k is equal to minus z d by dz, z transform of n to the power k minus 1. So using this result, let us find z transform of n. So to find z transform of n, we have to put k is equal to 1. If we put k is equal to 1, then z transform of n to the power n, which is nothing but z transform of n. This is equal to minus z as it is, d by dz as it is, z transform of n raised to, put k 1, so n raised to 0 we get. So now this is nothing but minus z d by dz of z transform of 1, n to the power 0 is 1. Now minus z d by dz of z transform of 1, we already know it is nothing but z upon z minus 1. So minus z, keep it as it is. Now z upon z minus 1, differentiate with respect to z. So using quotient rule, keep z minus 1 constant, derivative of z is 1, minus, keep z constant, derivative of z minus 1 is 1. So z minus 1 whole square. So here plus z minus z cancels. We are left with z upon z minus 1 whole square. Therefore z transform of n is nothing but z upon z minus 1 whole square. Similarly, we can also find the z transform of n square. To find the z transform of n square, we are using the same result and replacing k by 2. We already know the result, z transform of n to the power k as minus z d by dz of z transform of n to the power k minus 1. Here put k is equal to 2. So then we get z transform of n square, that is minus z d by dz, right hand side replace k by 2, we get z transform of n. Then minus z as it is, d by dz of z transform of n, we know it is z upon z minus 1 whole square. Now we are differentiating with respect to z. Keep minus z as it is. Differentiate z upon z minus 1 whole square with respect to z using quotient rule. Z minus 1 whole square constant. Derivative of z is 1 and keep z constant. Derivative of z minus 1 whole square is 2 times z minus 1 and divided by z minus 1 whole raised to 4. Now expand, take z minus 1 common from these two terms and simplify. You get z square plus z upon z minus 1 whole cube. Similarly, we can find the z transform of n cube. Here in the result, we can replace k by 3. We get the z transform of n cube. Now, let us see the property of z transform, that is the linearity property. If un and vn are any two discrete valued functions, then z transform of c1 un plus c2 vn is nothing but c1 z transform of un plus c2 z transform of vn, where c1 and c2 are constants. Now let us see two important rules of a damping z transform, that is damping rule. We all know that z transform of un is equal to u bar z. Then we need to prove that z transform of a to the power un, e to the power n into un is equal to u bar of z by a. That is, if un is multiplied by any function, that is z transform of a to the power n into un, it is nothing but u bar z by a. Similarly, z transform of a to the power minus n into un, we write it as u bar of az. Now let us prove first property. Now consider left side of a, that is z transform of a to the power n un. Now this whole thing we treat it as un. That is Z transform of un. Now, according to the definition, Z transform of un is what? It is summation n is equal to 0 to infinity un z raised to minus n. But here our un is nothing but a to the power n into un. So in the definition, replace un by a to the power n un and z raised to minus n as it is. Un keep it as it is. A to the power n into z raised to minus n, rearrange it and write like this, z by a whole raised to minus n. Now this becomes summation n is equal to 0 to infinity un z raised to minus n. So this we can also write it as u bar of z, but in place of z we have z by a, so it is written as u bar of z by a. Okay, next let us prove second property, z transform of a to the power minus n un. Now z transform of a to the power minus n un, again using the definition, we are writing it as summation n is equal to 0 to infinity a to the power minus n un into z raised to minus n. Un again keep it as it is, a to the power minus n into z raised to minus n, rearrange it and write it as a z raised to minus n. So again using the property of z transform, this is of the form un into z raised to minus n, which can be written as u bar of z. That is, in place of writing, in place of z we have az, so u bar of az. Now let us solve examples on damping rule. First example, let us find z transform of k to the power n into n. Now this is of the form z transform of a to the power n into un. Here a to the power n, in place of a we have k and in place of un we have n. So let us apply damping rule and solve this. So to find the z transform of k to the power n into n, we have to find z transform of n first. Okay, and in that result we are replacing z by a, that is replacing z by k. In place of a we have k, so z transform of n is nothing but z upon z minus 1 whole the square. So that is z transform of k to the power n into n. This is equal to, first find z transform of n. Z transform of n is z upon z minus 1 whole the square. In this result, we are replacing z by k. Why? Because in place of a, we have k here. So z transform of k to the power n into n is equal to, replace z by k. And here also in the denominator, replace z by k minus 1 as it is whole the square. Now z by k as it is you write, into simplify this, k square upon z by k, z minus k whole the square. Take LCM and simplify, and when you simplify this you get zk upon z minus k whole the square. So z transform of k to the power n into n, we get it as zk upon z minus k whole the square. Now let us find z transform of k to the power n into n square. It is similar to previous problem. Here in place of n we have n square, and here also we need to write the result of z transform of n square first, and in this result we are replacing z by k. So that is z transform of n square is nothing but z square plus z upon z minus 1 whole the cube. So in this result we are replacing z by k. That is z transform of k to the power n square is nothing but z square plus z upon z minus 1 whole the cube. Replace z by k. So now in the numerator replace z by k whole the square plus replace z by k. Similarly in the denominator also we are replacing z by k. So when you simplify numerator and denominator, we get the answer kz square plus k square z upon z minus k whole the cube. Similarly we can find z transform of k to the power minus n into n. K to the power minus n into n, it is using second damping rule. So z transform of a to the power minus n into un is nothing but u bar of az. So here instead of replacing z by a, we are replacing z by az. Okay, so to find the z transform of k to the power minus n into n, first we are writing z transform of n. So z transform of n is z upon z minus 1 whole the square. In this, we are replacing z by k, z into k. Okay. So, z transform of k to the power minus n into n, it is nothing but replace z by kz, replace z by kz minus 1 whole square. So, this is our answer. Similarly, we can find the z transform of k to the power minus n into n square. To find the z transform of k to the power a minus n into n square, again we are using second damping rule. But here, first we are writing the result of z transform of n square, and in that result we are replacing z by kz.